Okay, so there were two parts to this lab. The two experiments were both performed online using a PHET simulator. The experiment one involved me measuring the charge conservation for a series circuit that had resistance. There were multiple circuit configurations, as I'll explain further. In experiment 2, I was measuring the time taken for discharging and charging a capacitor using a battery and another resistance connected in series. I used two resistors primarily, a 10 ohm and a 20 ohm resistor in the form of a light bulb. Okay, so now let's move on to experiment 1. The circuit in experiment 1 is given on the side. The primary aim of this experiment was first to predict the current in both ammeter 1 and ammeter 2. So I predicted them both as 0.02 ampere. Why? Because I used Ohm's law, V is equal to IR, to calculate the total resistance, and then you applied it over here to find that the current should be same in both the amperes. Um, the experiment that I performed, the picture for that is given below, and that's exactly what I found. In the second part of the experiment, I replaced the one of the ammeters with a voltmeter. Now, what that I predicted what that would do is it would give me a 0 ampere reading in the ammeter, which is exactly what happened as shown on the right side. And there's a 3 volt reading on the voltmeter. There's a minus 3 volt because there's a difference between positive and negative. If you reverse the black and the red positions, it'll become +3. Now, why does this happen? This is because no current flows because the voltmeter is essentially like a resistor of infinite resistance. Therefore, it does not let current pass through and it only reads voltage. That's why it occupies all the voltage given by the batteries. That's why the ammeter shows 0 amperes as this current. The third part of the experiment involved measuring the voltages across different points across the circuit. So the one of the points was between the one resistor that is attached on the right hand side. The ammeter reading was 0.02 ampere as earlier shown. The volt readings across the different points are given on the left side. One thing to note over here is that the amp meter has zero voltage consumption, and therefore any point across A, H, G, and F will have the same voltage, which will be zero. Also, another thing to note is that the total voltage in the circuit adds up to 0 volts, which is what the law of conservation of energy says. So that's good. This is the exact diagram as to how the voltage is used. So between A and B, it increased because of the two cells having different voltages, 1.5 and 1.5 each. It decreased between C and D, which is the first resistor, and the second resistor E and F, decreasing the rest of the voltage, which is in again accordance with the law of conservation of energy and voltage. The Ohm's law was also used in the previous calculations. Now, why does the ammeter reading not change when you attach the voltmeter? That is because of the infinite resistance of the voltmeter. So when you connect a voltmeter in parallel to a ammeter, the current won't pass through the voltmeter and it'll only pass through the main circuit, therefore leading to a same reading in the ammeter. Um, the ammeter reading is 100 across the 100 resistor is 0.02 ampere because there's no change. So when I replaced it with a voltmeter, the current changes to 0.06 ampere. With an ammeter, the current changes to 0.06 ampere. This is because now with the ammeter in place, there are two points for the two circuits for the current to pass through. It's like a parallel circuit, and therefore it can pass through either of those, therefore leading to a change in the overall current because there are multiple paths. The resistance is calculated according to Ohm's law. From the observations I made earlier are given over here. So 47, first resistance has a resistance of 47 ohms. The second resistance has a resistance of 100 ohms. The wire has a resistance of 0 ohms because it's just an ideal circuit, and the ammeter has a resistance of 0 ohms because again this is an ideal circuit. In real life, this does not apply. The second experiment involved me charging and discharging a capacitor. So as you can see on the right, that's the circuit that I made. The bulb acted as resistance in the circuit, and the battery is a 9-volt battery. So what happens when the entire circuit is first connected and the capacitor is discharged? First, the bulb glows brightly, and slowly the brightness reduces, and the capacitor becomes fully charged. This is because the capacitor is becoming fully charged, and once it becomes fully charged, the flow of current stops. The current slowly reduces when connected with battery. When connected without battery, when connected directly to the bulb, if the capacitor is charged, it slowly starts discharging. So initially there's a very bright bulb, and slowly the lightness of the bulb starts reducing. The current also in turn starts reducing because the capacitor is getting discharged. um, these are the times it took for the capacitor to charge and discharge using the bulbs of two different resistances. One is a 10 ohm resistor and one is a 20 ohm resistor. um, the time dependency clause of the entire experiment is explored over here. So, as asked, a logarithmic graph between delta V across the capacitor divided by delta V naught, the initial voltage difference between the capacitor, is plotted with respect to time, and the following plot is obtained. The slope of the plot is found to be 0.086 as given in the diagram, and when you find the RC value, it turns out 11 point to be 11.63 seconds, which is exactly what the circuit also says, roughly about what the circuit says, which is around 11 seconds. And this makes sense because that's when the value of voltage is 1 by E times the original value. Okay, now let's move on to general questions that were given in the PDF. One is what happens if you're doing it in real life instead of the ideal situation. One thing to note over here is that there would be tons of internal resistance from the battery as well as resistance from the wires and the equipment itself. This would lead to a lower voltage and a lower current value than what should actually be there. So you would have to account for that. And what if a real battery was used to charge a real capacitor with no resistor in the circuit? What that would do is charge the capacitor instantly, but there will obviously be certain resistances such as the wire itself or the internal resistance of the battery that would slow it down a bit as compared to what happens in ideal world, which is what we were doing the experiment on earlier. The time taken to charge the capacitor will obviously increase because resistance has again increased, and that is why the measured time is different from the predicted time. That's all I had. Thank you.